First, I will explain how to calculate the potential energy in a uniform circular motion. For this problem, let's think in terms of polar coordinates, expressed as r, theta, and phi, rather than the Cartesian coordinates of x, y, and z. You can find more information about the polar coordinates in another video. This time, we will consider the radial coordinate r, which represents the distance from the origin in the polar coordinates. Here, we consider the central force such as gravity or Coulomb force, which is the origin of uniform circular motion. Because the force is always applied toward the center, the object is forced in the direction of -r. Thus, the force F is negative and can be expressed as F equals -k/r², where k is a constant. In the case of gravity, k is the product of the gravitational constant g, times the two masses, and in the case of the Coulomb force, k is the product of the two charges over 4πε0. Now there is an object at radial coordinate r. In order to move it away from the origin, energy must be applied from outside, because the force F acts on the object along with the negative direction. Thus, the potential energy can be considered as the required energy to lift the object up to a certain position. The potential energy for the central force can be calculated in the form of an indefinite integral, integrating -f at position r. Don't forget the minus sign before f, coming from the above definition. Substitute F to the central force, -r²k. Be aware that there is another minus in F that comes from the negative force. In the end, the two minus signs are cancelled, and by integrating k/r², it becomes -k/r, plus c, a constant of integration. The value of the constant c is arbitrary and cannot be determined uniquely without any additional condition. In the case of circular motion with a central force, it is difficult to define the potential energy when r equals 0 because the force becomes infinitely large. Therefore, it is common to define the potential to be 0 when r equals infinity. If we determine c so that u is 0 when r is infinity, c will eventually be 0, so the potential energy at position r will be finally -k/r. I mentioned earlier that the potential energy is hard to define at r equals 0, and we can confirm that u becomes -infinity when we set r to 0. Next, let's consider how to represent the total energy by m/r, omega. Since the total energy consists of the sum of kinetic energy and potential energy, we should calculate each energy. Kinetic energy is often written as T, and is expressed as 1/2 mv². In the previous video, it is proven that V equals R omega, so substituting this results in 1/2 mr² omega². The potential energy U can be represented as -k/r, as shown in the previous problem. To express the energy only using m, r, and omega, k is removed from the equation of motion. Mv omega equals mr omega² equals magnitude of F equals k/r². If you move one r from the r squares to the left, you will see that k/r equals mr² omega². Substituting this in the equation of u equals -k/r, we obtain u r as -mr² omega². Thus, the total energy E is equal to the kinetic energy, 1/2 of mr² omega², plus the potential energy, -mr² omega². You may notice that these two terms have the same physical dimension. The final result is -1/2 mr² omega². Note that the potential energy equals twice of the kinetic energy with a negative sign, and the total energy equals to that with the negative sign. Thus, there is a beautiful relationship between the amount of kinetic, potential, and total energy, which is called the virial theorem, which often appears in quantum chemistry.